Hello everyone, my name is Ana Carolina and I am a PhD student and I will present this research paper Rheological study of ethane gas hydrates through a high-pressure cell with Gustavo Alonso. My advisor is Monica Nakashi and he are the other authors. The outline is divided into these 5 parts. So, gas hydrates are known as crystalline structures composed of water and gas. These crystalline compounds are similar to ice and form when the water-hydrogen bonds engage and retain one or more molecules under appropriate thermodynamic conditions of high pressure and low temperature. The molecules that are usually captured are gases of low molecular weight as carbon dioxide, ethane, methane, and natural gas. In the figure on the left, we can see an example of hydrate accumulation in a cold layer. Hydrates have found important application in refrigeration for gas storage, as an energy source, as alternative form of gas transportation, as we can see in the figure on the right, and as a principal cancer in the flow assurance in the production and transportation of hydrocarbon fluid in offshore subsea operations, and as we can see in the figure on the left, the hydrate plug formed in a subsea hydrocarbon pipeline. This topic is the focus of this particular research. And on the right is a figure of a hydrate slurry formation at a laboratory scale. The main objective is analyze the ethane gas hydrate formation from the rheological point of view, and the specific objectives are to study some conditions and determine the pressure drops and the amount of gas consumed. The experiments were conducted in a shear stress controlled rheometer hack Mars 3, as we can see in the figure on the left. The rheometer is connected to a thermostatic bath. The pressure cell was designed to be used with the hack rheometer. The cell consists of a rotor and a stator. The pressure cell contains a needle valve, as can be seen in the figure on the right, which can be closed at any time during testing. The main components of our emulsions are the ionized water, mineral oil, and SPAN 80 as a stabilizing agent. SPAN 80 is an important surfactant that acts as an important antiglomerant agent for hydrates. Thus, it is important to consider this property of SPAN 80 as a hydrate inhibitor. The water in oil emulsion were prepared using the following methodology. Step 1. Weigh the required masses of SPAN 80, deionized water, and primal oil. Step 2. Magnetic homogenization of SPAN 80 with primal oil at a speed of 1000 rpm for 5 minutes. Step 3. Addition of water in the mixture of SPAN 80 and primal oil. And Step 4. Homogenization of the components obtained in Step 3 on the Tullux mechanical ester at speed of 10,000 rpm for 5 minutes. The emulsion stabilization up to 2 hours. The gas selected to conduct the experiment was ethane. Then, as was mentioned earlier, ethane hydrates can form at moderate pressures, for example at 2 MPa and 4 Celsius degree with a subcooling of 8 Celsius degree, as we can see in the equilibrium curve on the right. The subcooling can be variable in tests. On the graph on the left, we can see the saturation curve, which shows that during our test, ethane remains in the gaseous phase because we work in the test with a temperature range of 25 Celsius degree to 4 Celsius degree, and with a hydrate formation pressures always around 2 MPa. Once the experiment is initialized in the rheometer, the cell begins to be pressurized with ethane until it reaches an initial pressure of 25 bar, and the pressure will change during the test. From now on, Gustavo Sandoval will present the results of the test performed.
Okay, now I'm going to explain the results obtained with the system presented above. Our results are exhibited through viscosity curve as a function of the experimental time, and also on the right axis of the figure we can observe the temperature that is represented by the red line. Initially, our experiments were conducted at 25 degrees Celsius for 4 hours. This step is known as the dissolution period and is when the gas dissolves in the emulsion. Then the temperature is reduced from 25 degrees Celsius until 4 degrees Celsius at a constant cooling rate of 0.6 degrees Celsius per minute, and this final value of 4 degrees Celsius remains constant until the end of the experiment. Most of our tests were conducted at 30% water emulsion with ethane and with closed valve throughout the test. That means that the cell is pressurized until achieve the required pressure, and then it is consecutively closed. Okay, under condition of 4 degrees Celsius and pressure higher than 8 bar, our system is under the region of equilibrium of hydrates. Our first experiment was conducted with pressure of 30 bar with 1.43% of span 80 and on a constant shear rate throughout the experiment of 401 over seconds. As observed, by the results is represented by the blue rectangle. We can observe that the viscosity decreased until attains a final constant value of viscosity. Then the viscosity increased due to the reduction in temperature, and the viscosity attains a final value that remains almost constant until the end of the experiment, showing no hydrate formation. As a drastic and spontaneous increase in viscosity was not observed, we see the characteristic behavior caused by the agglomeration of hydrate crystal. Then, to increase the driving forces for hydrate formation, the experimental conditions were changed. First, the pressure was increased from 30 bar to 35 bar, and then and also the shear rate was also increased from 401 over second to 701 over second. The amount of surfactant was also decreased until achieve a required value that permits hydrate formation. And then in this condition of pressure of 35 bar and a shear rate of 701 over second, another experiment was conducted with 0.76% of span 80. As noted in the gray curve, hydrate formation also did not happen, despite the viscosity was lower in comparison with the first experiment. Then another experiment with 0.22% of span 80 was conducted. This is represented figured by the orange curve. And as observed, after 20 hours in the condition of hydrate formation, a small spike in viscosity was noted, indicating some agglomeration of the hydrate crystals. Then in another attempt, other experiment with 0.08% of span 80 was performed. We can observe in figure that the viscosity during the dissolution period was the lowest in comparison with the other experiments, and after 17 hours of the experimental time, hydrate formation was observed as a drastic and spontaneous increase in viscosity was noted. The viscosity was 7 times higher at the final value in comparison with the prior value at 4 degrees Celsius, indicating hydrate formation. Finally, another experiment was conducted without span 80. This system is known as non-emulsified system because does not have surfactant, and as observed in the black curve, hydrate formation also was not observed. And maybe this is due because our geometry, that is concentric cylinders, don't not generate the necessary conditions or necessary mixture to be all the hydride constituents to be in contact. And this topic will be studied in future experiments with another geometry. In order to show a new formation but in short induction time, a second test was carried out with 0.08% of surfactant in the emulsion, but in this case the working temperature was reduced to 1 degree Celsius to have more severe conditions for hydrate formation and reduce the induction period, that in our case is defined at the time measured from the system when passed through the hydrate equilibrium curve until the moment of hydrate formation that is represented by increase in viscosity or decrease in pressure. In figure, we can know the viscosity, the experimental time, and the sharp right axis between pressure and temperature. The filled symbol represents the viscosity, the empty symbol represents the pressure, and the blue curve and the gray curve represent the second experiment. Initially, the pressure increased until 35 bar. Then at this moment, the needle valve that is attached to the pressure cell is closed. Then the gas begins to be consumed during the dissolution period. Then the pressure drops. The pressure continues dropping during the cooling step until the induction period, where the pressure remains constant until the moment of hydrate formation, where the pressure also decreased due to the consumption of gas during the reaction, and it is caused by the water hydrogen bonds captured and retain more gas molecules that produce the pressure drops. This did not happen for the first experiment, maybe because the formation happened so quickly that the pressure sensor didn't know get to capture this behavior change. If we compare both experiments, we can know that the consumption rate during the dissolution period was different. The difference here was around 3 bar, but this difference was similar in the induction period. That means that the consumption during the cooling state was very similar. As noted, the formation of hydrate was similar times, and maybe this is due to the supercooling degrees are very similar in around 1.5 degrees Celsius. And as noted, the temperature for the second experiment was lower than the first experiment, but the pressure also was lowered from the first experiment. So the supercooling degrees was very similar in 1.5 degrees Celsius, and maybe this explains why hydrate formation happens at very similar times. Once the amount of surfactant to obtain our emulsion was determined and the thermodynamic experimental conditions for the hydrate fluid were defined, our next step was to conduct different experiments varying the amount of gas that entered inside the pressure cell. To this end, the needle valve that permits the gas inlet in the cell remained open during different periods of the dissolution time. As noted in figure, 2 more experiments were realized allowing the gas inlet inside the cell. One of them, represented by the orange curve, was conducted leaving the valve open during 2 hours of the dissolution period. The other experiment was performed with open valve throughout the dissolution time, is to say, during the first 4 hours of the experiment. The previous result showed with closed valve throughout the test were also plotted for comparison reasons. If we analyze the induction period among the experiment, we can note that the experiment conducted with closed valve at the beginning of the experiment took around 11 hours to form hydrates if we measure the induction period from the 5th until the 16th hour of the experiment. The another experiment conducted with 2 hours of open valve took around 5 hours to form hydrates, but also we need to observe that the supercooling degree for this experiment was higher in comparison with the first experiment. Regarding the experiment conducted with 4 hours of open valve, we can know that hydride formation occurs as faster as the system reaches the temperature of 4 degrees Celsius, and the viscosity increases higher than the maximum Rheometric allowable torque was attained, and when this happens, the viscosity drops and the experiment must be stopped because the magnetic coupling between the transmission is lost. Another important information that we can take from the results is the amount of gas that is consumed during the reaction of hydrate formation. If we know the pressure, temperature, and system volume before hydrate formation, we can calculate through the equation of state of real gases the number of moles in this point. If we apply this same equation after hydrate formation, we can calculate the difference of number of moles consumed in the reaction of hydrate formation. This information is important, and the number of mass consumed during the hydrate formation for the experiment conducted with closed valve was around 2.4 grams, and with the experiment for 2 hours of open valve was around 1.7 grams. That means that the experiment with closed valve took more time to form hydrates, but also consumed more gas during hydrate formation in comparison with the results of the experiment conducted with 2 hours of open valve. Okay, now I'm going to enumerate some final remarks. Hydrates formation was noted but a random and abrupt increment in the viscosity. It was verified that span 80 acts as a hydrate formation inhibitor. With the methodology presented for hydrates, it is possible to calculate the amount of gas that is consumed during the hydrate formation, and the induction time is affected by the amount of gas presented in the cell, probably due to the increment in the subcooling degree. We would like to say thank you to Petrobras, CAPES, NPK, and Puquijillo to allow us to conduct this work. We would like also to say thank you to the organization event, and if you have any doubt, please let us know.